So once you have your hypotheses, step 2 is when you actually look and figure out how unusual your p-hat is, what you got in your sample, your observed value. So you can see here, we create basically a z-score. It's called a test statistic, but this is basically looking at if the mean is really at whatever that hypothesized value is, how many standard deviations away is our p-hat that we observed. That's all our z-score is. So you got, if this is the real mean, there you are, right? Because it's usually x minus mu all over sigma, and there's that standard deviation. So that's all that stuff from 6.1 in terms of our mean and standard deviation. All right, so then we can get our z-score. And then after that, we can also find our p-value. And just like in our example with the coin tossing and the trash with the roommate, our p-value is this tail probability, theoretically a tail probability. So if we're doing a right-tailed test, oops, that's a terrible drawing. For all of our tests, oh, those are terrible, just pretend. Our center is going to be our null value, because we're hypothesizing that's the real thing, and we know the mean of a p-hat is at real p. And for a right-tailed test, if we have this, you have some p-hat that is larger, right? That gives us evidence, just like we saw in our example with the coin flipping. We said we think p is greater than 0.5, and we had a p-hat of 0.6. So you have a value off to the right, and then we wanted the probability off to the right as well. If you're doing a less than test, you're doing a left-tailed test, you should end up with a value that is less than, so that way it's giving you evidence of what you want. And we're then looking for a left side probability. And the only one that's a little bit different here is our not equal to. If I just want to show something is different, it's about being more extreme. So if we happen to have a p-hat that is larger, we're going to go to the right-hand side, but we're also going to go to the left-hand side a symmetric amount as well. That's our two-tailed test. So if our p-hat had been negative, no matter what, we're going to be going away from the average. So you'll notice all of these tests were called a right-tailed, left-tailed, two-tailed, because we're always should be looking at the tail as opposed to the body of our distribution. So the meaning of this p-value, this is why we spent so much time on conditional probabilities in part 4, because it's a conditional probability. So it is the probability of observing a test statistic this extreme or more extreme, observing a sample this extreme or more extreme. So here's your sample value, something more extreme, if there's the given, the null is true. So our p-value is all given h naught is true. This is where the court case example comes in. Assuming the guy is innocent, let's look at our evidence that we have. So this is basically, what's the probability that we have this evidence if he's actually innocent? So like, what's the probability we have his DNA at the scene and a motive or whatever if he's really innocent? And the big idea here is a small p-value indicates that something is unusual or unlikely to happen if the null is true. And then we're in the same situation as our example with the coin flipping. There's two possibilities here. Either we got really lucky or there's something hinky going on. And this is the same idea that we had actually with the idea with, what's her face? Joy, right? We made the assumption, we assumed she was guessing. And so we just went and pretended to smell those 12 shirts, right? And then we figured out the probability of getting 11 or more shirts if that we were just guessing. And this ended up being really, really small, so we could say, well, either she got insanely lucky on her one-time guessing, or she can actually smell Parkinson's. So here's the p-value in terms of finding it. So first things first, a lot of times it is helpful to visualize these things. So if we're talking about z-scores, we're talking about standard normals. Loop. The first one, we're doing a left-tailed test. So that means our alternative was that p was less than some value. So once we get out this z-score of negative 2.46, we'd be interested in the left side. And if you want to find that probability, you could, of course, use normal CDF. The lower bound of our standing for negative infinity up to that 2.45. Or 2.46 with a 0 and 1 as our two values. But here's where I actually think the tables are going to be a little superior. If we have already a z-score, that's exactly what the table is set up for. In fact, remember the table, we saw it way back in the day. My cat is playing with the screen. The normal table gives a left-hand side probability. So if we go over to our normal table, so past the t table to our normal table, and we were looking for negative 2.46, I think. I might be wrong. We'll figure that out when I go back. That's a lot quicker than writing a bunch of stuff into my calculator, especially because we will have this on the test. So there's our p-value, 0.0069. 46? Yes. 0.0069. So a very small probability, which makes sense because we were dealing with a z-score that was very unusual. All right, so right-tailed test. In this case, our alternative would be that p is greater than some value. Whatever value we got out from our distribution was 1.65 or 1.67 bunny hops above average, and we want to know about getting something that or more extreme off to the right. So again, we could do a normal CDF, or we have our two options in terms of looking at our table. If I look at my table, 1.67. I forget as soon as I walk. My cat keeps touching the freaking screen. I'm gonna kill her. Stop it. What are you doing? There's nothing fun here. 1.67. Oh my god, there's nothing fun on the screen. It is just math. So if we go to 1.67, nope, stop it. We can go over, figure out where this is. Trying to get off the thing. 0.9525. The one thing I'll say here is if we do that, remember this is giving us the left side probability. So 0.9525 is over here, and we need to do a 1 minus. So this is where I have a shortcut if you're going to use the table. My shortcut if you're going to use the table is always one. Look up the negative z-score. My reasoning here is if we're talking about a tail, right? Tail, our z-score, our p-value, right? Our probability should always be less than 50% if we're getting out a tail. So instead of looking up whatever the heck our z-score was, we would in this case look up negative 1.67. The previous problem, well, it was already negative. So if we did this, we're just going to look up negative 2.46. So this doesn't mean change the sign. This just means only look at for p-values. We could basically just take this table here and ignore it because everything here is bigger than 50%. And we'll just look at this. So 1.67, the negative version, we won't have to do the 1 minus. It's already been done. 0.0475. So 0.0475. All right, the last one, which is why this has a step 1, is our two-tailed test. So if we're doing a two-tailed test, now we have, this would be something where we're looking at p not equaling a value, and this is the most difficult. So in this case, it looks like our z-score is negative, so our p-hat was below average by 1.3 bunny hops. And since this is a two-tailed test, I not only care about this area, I also want to go an equal amount to the right, assume that is equal, and look at that area as well. So my p-value is going to be both of these things added together. So there's my step 2, is not only look at the z-score, that's the negative side, but then multiply by 2 if we're dealing with a two-tailed test. So in this case, I'm just going to look up the negative 1.33. If this had been positive, I'd still look up the negative. That is not what I want. Come here. 1.33 0.0918, and that's this left side, 0.0918, which means this right side is also 0.0918, and our p-value is just going to be 2 times 0.0918, which is 0.1836. Alright, so if we write down what we did, we're going to look up negative 1.33 and then times 2 because we're doing a two-tailed test. So again, one thing you do want to see here is always your p-value should end up, oops, that is not what I meant to do. Should be less than 50%. There are obviously times when this will not be the case, but for the most part, we're looking at something unusual and trying to say, is it unusual enough?